Thank you very much, Andre, and I'm very pleased and privileged to address this very distinguished group, Victoria Probability, and I'm glad to have the opportunity. So you can see my title here. I think you'll see what it means as we go along, and I should acknowledge my co-authors, Yuguang, who is now in Melbourne, and Shemehsavar, who's at Tehran.
Sorry, boss, could you make it full screen, please?
Well, I'd rather do it this way. The reason is
okay.
I experimented with this. Here I can make some emphasis this way, and also I'm able to scroll. The other full screen, I couldn't do this. So is this very visible enough for people?
Yep.
Yeah.
Yeah, I think you can see it. So yeah, okay. Number of species in the negative binomial process model. So we have a history going back a few years now of working on this model, and which I don't want to go into because it's very detailed and technical, but the upshot of it is that we came up with this model that we call PD alpha R for species, let's just say species distribution. And it's a generalization of a model due to Kingman going back to, I think, the 1970s in the last century, as it is, which would now be known, would now be known in one way as a PD alpha model. Our model has two parameters. This alpha is in 0, 1, and this R is a positive, any positive number. So for this model, in the previous publications, we have a version of what's known as Ewens sampling formula. And we calculated formulae, for example, for the mass function of the Kn, which is the number of species that appear in the model in the sample of size n. And what I want to do in this seminar is sketch a derivation of the large sample distribution of Kn as n goes to infinity, and in doing so, bring in the connection with this so-called Dickman distribution or generalized Dickman distribution. So the sort of data that we're looking at, I can use this little critter here to motivate the data. We found this in the literature. This is a quoll, cute little guy. It's a carnivore, actually, about the size of a cat, and occupies a very similar niche in nature. In other words, it catches and eats things smaller than itself. It's an endangered species, and as we look through the literature on this, we managed to find a little bit of data, in particular from this paper of Firestone et al., which is listed in the references. So it's just an example of the sort of data that you can see. And
Ross, sorry, there is a question. Asking, will Kn not go to infinity as n goes?
Kn certainly goes to infinity as n goes to infinity, yes. Yeah.
Then what does it mean, asymptotic distribution?
Sorry? What was the question?
Yeah, State, ask your question.
Normalize Kn, or what will you do?
I'm sorry, I can't hear the question. Can you speak up a bit? Who's speaking? I can't see who's speaking.
State, okay.
I will say, or you will say, Andy?
No, you say. You say, okay. But louder.
Okay. So this Kn will be normalized, standardized, and that's what you are talking about?
We will definitely come to that, yes.
Okay.
Yeah. So this is by way of motivating the sort of data. If you look across here, you see some MJs, and the interpretation of these is this is actually alleles, genetic data. And so, for example, there were two alleles of a particular type, which were found in one so-called diploid pair. And these diploids, there's two of them per animal. So there are in fact 15 animals in this sample. That just about exhausts my knowledge of genetics. So, at least we have this set of data here. So 2 alleles of a particular type, 90 is just an identifier, 106 are identifiers. 2 alleles were common to exactly 2 pairs of 2 diploid pairs. 3 alleles were common to 4. 1 allele was common to 9 of these diploid pairs. So what you're seeing is common alleles at the right-hand end of the table and rare alleles at the left hand. It's the kind of data that we want to analyse. So these MJs are the observations that we're interested in. If you take J times MJ, you'll get 30 alleles. So that's a sample size of 30. That actually corresponds to 15 animals. As it happens, a very small sample. The number of allele types here is given by adding up the MJs, and if you add these up, you'll get 9 different allele types in the sample. I'll just mention that the zeros here can be omitted. They have no significance. In fact, you could also pad out the table further to the right by adding in zeros. There are 0 with 10, 0 that appear in 10 alleles and so on. The Firestone paper is conservation. These are environmental biologists, and they're interested in the conservation of the species. As you can see, we're looking at very small samples. This quoll is a threatened species, and data on it is very hard to come by. That's not really the point as far as we're concerned. I want to do asymptotic analysis, but you can see that you can see from this small data set the sort of thing that we're looking at. So to formalize this, I want to use some notation. So those MJs I will collect into a vector, boldface MN, and the entries in the MN of the number of species having allele type J in the sample. If I add up the MJs, the total of the vector M, then I will get the total number of species, and that is Kn, and it depends on the alpha and R that we assume for the underlying model. Mn alpha R takes values among n vectors of non-negative numbers, lowercase m, with the constraint that J times summation J times Mj equals n, which is the sample size. And Kn, which is the summation of the MJs, of course, takes values among the integers, the first n integers. In this earlier paper, we described the joint mass function of the M and the K taken together in this form. Now, I don't want to go into where this comes from because it's rather technical. And I think you'll also agree that it's rather ugly. And part of what I'm going to do today is pick this apart and try and show you how we can make some sense of it. Just before we leave it, make a couple of points. This RK here is the so-called ascending factorial. Lambda is the variable of integration. The integration runs from 0 to infinity here. There's a function psi on the bottom, which I'll mention in a minute. And here, this part, we have a kind of a, you can observe a kind of a plus-on looking component in this. If there had been an E exponential term in here, we would have the plus-on probability. And in fact, I'm going to put that E in there in a minute. The MJ here, remember, are subject to a constraint, and so we take the set I'm calling A and K is the sum of these M's such that J times M, J adds up to N, and the MJs add up to the K, which is the variable here that we're looking at. The two functions, psi and f, are given by these formulae. And the critical point here to note is this x to the minus alpha minus 1 term. This, you can see this is a kind of a Laplace transform. And the x to the minus alpha minus 1 appears here as a result of the fundamental way that the distribution is constructed from a stable subordinator. And that alpha, which lies between 0 and 1, comes from that stable subordinator. There's also the parameter r, and I'll mention a little bit later where that comes from. The other functions are the f's, which if you look, you can see are essentially the derivatives of the psi. It's got an x in here, and the e to the minus x comes in here, and you don't see a lambda because I changed the variable here to lambda, and I guess I factored it out here or some such. But anyway, this is the definition of these two functions. We're interested here in the distribution of the Kn. I don't want to have to talk about the m's in this exercise. So we have to add out over the vector lowercase m, which you'll remember is constrained to be in this set of the a's here. So the formula for k takes this appearance here. We still have this stuff in the front here. Now we've summed up this product here, which is virtually a summation of Poisson probabilities. And maybe I should mention at this point that the underlying model is not Poisson, it is negative binomial. And we will see the negative binomial appear a little bit later. So despite the fact that we see Poisson type probabilities here, that is not actually particularly relevant to the end result. But I will use this fact in the analysis. So I have to introduce another quantity that is a subordinator. It's a yt is a process in time, and it depends on lambda. So for each lambda, I have a subordinator yt whose Laplace transform, the Laplace variable is this tau, is given by this formula here, and you can recognize here essentially the Levi-Kintschen version of the exponent of the subordinator. The Levi measure that's involved here also depends on lambda. Well, that in fact is the dependence on lambda, and is of this form. Once again, we see the power here, y minus alpha minus 1 appearing, and the Levi measure is restricted to lie in these intervals here, which depend on the lambda. So the issue here is whether lambda is bigger than 1 or smaller than 1. That defines a certain Levi measure. Again, you can see it's a kind of a modification of the stable density, the stable Levi density. Actually looking at a density here rather than the measure. As a random variable, each of these yt lambdas has a continuous bounded density, and the notation I use for that is a lowercase f and the subscript of the random variable that we're talking about. Hello, David, I see you joined. Welcome. So that's most of the notation that I want to set up here. And this is the equation that I want to analyze. This is this formula that I want to analyze as n goes to infinity. You can see that it's quite ugly, and we have to figure out how to deal with this. We do deal with it, and in fact, here's the answer. As Estarte observed, we're going to need to normalize this. The Kn tends to infinity with n, and we need to normalize it, and the normalization is n raised to the power alpha. And when we do that, we will get an asymptotic, we'll get a proper asymptotic distribution for this Kn, which is of this form here. So let's just take a minute to examine what's in here. There's a couple of constants here, gamma functions. Two integrals here. The inner integral with respect to lambda And the lambda appears here. Remember, this is in this subordinator. Lambda appears here. It appears here. And it appears here. And we have an outer integral with respect to x. The x appears here. It appears here. So the x here is the time parameter, if you like, of the subordinator. And x also appears up in here. Now, your immediate response will be, this is a horrible looking thing. Is it in fact a CDF? It is in fact a CDF. And that will be part of, showing that fact will be part of the proof. So I'm going to go through some of the steps. Sorry about that. I think that's my, do you still hear me now? Yeah, I think that was my silly telling me to take a break. We have these kindergarten rules here that you should take a break every now and then. So I turned that off. Hopefully you can still hear me talk. But I can't hear you, so remind me I should turn it back on again when you want to speak. Steps in the proof of theorem. Maybe that didn't, actually maybe that doesn't help, does it? Excuse me. Steps in the proof. My only excuse for going through some of this technical detail is to show you how we will arrive at this Dickman function. Proof requires some fairly extensive analysis. Formula 1 appears far from transparent. I think you'll agree with that. It's not even clear that 1 defines a proper distribution. It is so, in fact, and the proof of, to prove that, you can, one way of proving that is to use this Farder-Bruno's formula, which is a way of differentiating function of a function. So if I go back to equation 1, people that are familiar with that might recognize the summation on the product as being a clue to that, you might need to use Farder-Bruno's formula. It is in fact a proper distribution. We observed a Poissonian component in it. We add out over that Poissonian component, and that is going to give us a Poisson probability. And because of the constraint, I'm going to denote those Poissons by nj lambda. Because of the constraint, that probability takes a form summation j nj lambda equals n. Remember that the j summation j mj had to add to n, and the summation of the n will have to be equal to k. I'm sorry, this thing is going to keep doing this, and I don't know how to stop it. And to make it a Poisson, as I mentioned, I have to bring in this factor of the exponential just to make things the same again. And I still have this thing in the front here. So that's just a rewrite of Formula 1. Does anyone know how to stop that? Do you hear that? I suppose you must.
Yes, we hear, but it's okay.
Okay. It's an annoying thing that tells me I should take a break and have a cup of coffee or something.
So it's all fine, Ross, it's all fine, provided they will not fire you for not taking a break, right?
I would if they could. We can go into that later. So what I'm doing is stepping through this, and so I have this joint Poisson probability, and I want to write it as a, I want to condition out on the summation of one of the Poissons, and that will leave me with, in fact, a multinomial. If I condition marginally on the sum of the Poissons, then I will be left with a marginal. And so I now have a capital M coming in. Summation of the JMs is equal to N. And this M is multinomial with parameters K and the probability that corresponds to the Poisson probabilities, which are now normalized, and that was these Fj lambdas. And I still have my exponential here, and I still have my function in here. So now from number 4, what will I do? steps in the proof. The unpromising looking first factor under the integral sign, by which I mean this, this bit here, actually, if you look at this long enough, you can see that it is very close to being a negative binomial probability. So I will define a negative binomial probability. Negative binomial random variable has parameters r and 1 on psi lambda. That is in fact a probability. And we have this probability of the neg bin equals k. And because it's not quite right up here, this is not quite the negative binomial, there is a factor, an extra factor that comes in. I'm just calling that ln of lambda, which in fact will be quite easy to deal with. So I turn the unpromising looking factor into a negative binomial probability. I turn the Poisson into a multinomial, and with all the changes, I'm left with the d lambda on lambda here for this lambda integral. Now, a useful trick which I found in a paper of Jeff Watterson's, although of course it's elsewhere in the literature as well, is the following. You can write a multinomial probability as a probability involving a sum of IID random variables. So this probability summation Jmj can actually be written as a summation from 1 to k now, k here, of xin lambda, and still retaining equals n. And of course, the reason for doing this is that we know lots about limiting behavior of sums of IID random variables. Actually, it's a triangular array of IID random variables because the distribution depends on n, also depends on lambda. So I was able to, or we are able to, turn this probability into something a little more tractable, involving a sum of IID random variables. And they're discrete random variables, and the mass function again is this PNJ, which appeared earlier on with regard to the multinomial. So that's another reduction. Next step is to rescale Kn. So you can look at the equation, whichever one it was, for quite a while, and still wonder how you're going to get the limit with n. The scale factor, as I mentioned, is going to turn out to be n to the alpha, and there's another trick which is needed, which is to change variable from lambda to lambda n. How did we arrive at this scaling by n to the alpha? Not at all obvious at first, and you might think also that it should depend on r. After all, r is another parameter in it. But it turns out that the correct scaling is n to the alpha, and that comes about, well, or at least you're led to conjecture this, because that is the correct scaling in Kingman's original PD alpha model, which I'm not sure I mentioned it in these terms, but that was the original model that came out in Kingman's original Poisson-Dirichlet paper, where he takes his subordinator to be the stable alpha subordinator. The correct scaling by n to the alpha, that's given in Pitman's book, and it's relatively simple there to deal with this Kn, divide it by n to the alpha, take the limit, because the distribution there is written quite explicitly. When you divide out the n to the alpha and take the limit, you get a Mittag-Leffler distribution. And that's the way of doing that is written out in Pitman's book. Not quite sure who first proved that, but you'll find it in that book. So what we're looking at now, we also have to do this variable change, but having done that, we now have the probability of the x's. You'll observe that this is a kind of a local probability, and we have the probability of the negative binomial. We've got this extra bit in here. We want to write 5 in the form of a CDF, so this is the mass function. we bring in the factor n to the alpha here and write this as a CDF, and that's straightforward trick in doing that. And what we end up with now, that will so we've got to sum over this sum over the mass function to get the CDF, and that can be written as an integral. So that's where the dx integral comes from. The k's that were in the previous formula now become xn to the alphas. So that was a summation of k, now summation xn to the alpha. Negative binomial, again, the k here. So this is the function, the formula that we have to deal with now. And we want to show that this will have the limit that I have in, I think it was equation 3 back there. So we need to find the limits of these functions. We do that individually, the L, the X, and the negative binomial. We find those limits individually, and then we have a problem of taking the limit under the integral. The correction factor is easily found. It turns out to be an exponential. I won't go into the details, just a ratio of a couple of essentially factorials. And also the negative binomial probability, if you write it out, it's just some factorials. And you can use Stirling's formula to get the limit. It turns out that the n to the alpha, the lambda n here, is exactly the right scaling to give you the limit for the negative binomial. For the x's, as I say, we have a sum of a triangular array, but we need a local, so we're going to appeal to usual asymptotic theory, going back a long way back to Gdenko, Kolmogorov, or even earlier than that, to get the limit of the sum of the x's. But we actually need a local version of that because we have this summation equal to n here. We don't have the CDF. We have a local PDF version of this. So what we have to do is derive this local version. That's rather technical. I'm not going to go into how that's done. In fact, it's very standard. You write down, if you know how to prove the local limit theorem for asymptotic normality or any of these stable laws and so on, you write down the characteristic function of what you're looking at. You invert it, you write a Fourier inversion, and then again, you've got another limiting problem to deal with to take the limit under the integral, but that can be done with quite a bit of technical checking. And what you get there is convergence to that subordinator that I introduced in number 2. And notice that effectively we're looking at a functional version of this. We have xn to the alpha up in here. If you remember back in my solution formula, we have the subordinator y. Well, maybe I can quickly, go back to that? Oops, too far, there's the quoll. Might be too much to hope that I can find it. Here's our subordinator. And okay, so here's our subordinator y, and the time parameter here is the x. All right, so the significance of that is, so that's where this comes from. That's the x there, and the limit of the sum is going to give us an infinitely divisible distribution, but we have the functional version of it depending on x, and so that's where the subordinator comes from in that formula. So we have found we have found the limits of the functions in the integrand. We have to take the limit under the integral, and when we do that, we will indeed get the formula in number 3. So all we have to do is justify taking the limit under the integral. We spend a lot of our lives as probabilists, we spend a lot of our lives taking limits under integrals, and we know how to do that. We use the dominator convergence theorem, and we have to get the bounds and so on. That will work. Well, This, if you take a look at this integral here, the bit that matters is d lambda on lambda. It's singular at 0 and it's singular at infinity. So the bounds that you get for dominator convergence are going to have to apply uniformly and so on. You can spend a lot of time and a lot of scrap paper trying to get trying to justify that interchange by finding bounds on those separate terms in this integral. That turns out to be just too hard. But there's a better way to do this. There's a better way to do it, and the way to do that is to show that, in fact, the limit function is indeed a proper CDF. In other words, that it integrates to 1. And if you can do that, there's a simple argument, or a relatively simple argument, that you just uses Fatou's lemma in 2 directions. You can use it to show that indeed what you'll get for the limit of your left-hand side probability is what you see by taking the limit under the integral. You can, there's a simple argument for that. So the problem now boils down to showing that this expression here, the limit of that whole thing, is equal to, when I integrate over the whole range, x is 0 to infinity, that integrates to 1. And my point of, my reason for taking you through this rather painful analysis is that this now brings in what I think is a very interesting aspect of the so-called Dickman, generalized Dickman function. And to do that, I have to say a little bit about how we derived this PD alpha R model, and it's based on a negative binomial point process, which was invented by Gregoire, author Gregoire, back in 1984. And without going into too much detail, the measure associated with this point process is this one. And of course, you will recognize this as what we've been seeing earlier as essentially the stable density, but now truncated to the region 0 to 1. So I think if you think back, you can begin to see how these expressions will have arisen because of this point process, particular point process measure here. And when you go back to Kingman's formulation and you work through what they did and the kind of working that is in Pittman's book, for example, and well, a lot of the other literature as well, you see that what you should do is add up the points in BR in this point process, which I'm calling alpha RT. That this thing has a density, lowercase g, depends on alpha and r, and it has a CDF, capital G. And I said that I'll skip a lot of technicalities. I don't want to show you the formula for this. It's not all that hard. You can write down its Laplace transform quite easily. It's quite explicit, but I don't want to have to do that. But what I will do is say that from it, you can easily check that there's this kind of reproducibility formula for these sum of this point process, which takes the following form. If you take a t with alpha and r and a t with alpha and s, and you convolve them, independent copies, then you will get a t with alpha r plus s. Quite nice. And then if you go back to number 3, which you remember is our solution, you can write it in this form. Where does that come from? Well, that number 3, you'll notice that it breaks up into, if I break it up into lambda less than 1 and lambda greater than 1, this just becomes e to the minus x. I can actually do one of those integrals explicitly. The other one I can't, but what I can do is show that the integrals that you get with this procedure are of this form. So this lowercase g is this density of this sum of the negative binomial points, and the capital G is the CDF. The integral on the right-hand side of 3, taken over the whole range, is of this form. And what we want to show, you'll remember what we want to show is that this equals 1. So that means that I have to show that this equals 0. And that's the task of the rest of the seminar. So I hope I can get through. And this is where we introduce the generalized Dickman function. Now, the Dickman function arises in number theory, and it's known to arise in this context. It's mentioned, for example, in Andrew's book and in some of his papers. I'll give a reference to the book later. And it is it arises in Pittman's book as well, in connection with the Poisson-Dirichlet process, which is treated there. So what is it? Well, my knowledge of number theory extends to, you see this thing is getting even more insistent. If you take the number of positive integers less than or equal to a certain number with no prime divisors greater than a certain number, in other words, it's something to do with small prime divisors of numbers, and you normalize that in certain ways, and you take a limit, you get this thing called the Dickman function. And as I say, that pretty much exhausts my knowledge of prime number theory, other than except that I do happen to remember there's infinitely many primes. But apart from that, the Dickman function has this subordinate, well, we can make a subordinator by introducing a parameter A, which you see is the time parameter of the subordinator, and it has the Levy-Khinchin representation of this form here. So YA is a so-called Dickman subordinator, where the time parameter is a constant A here, and its Laplace transform is of this form. And you see, you note the remarkable simplification here. Here we have dy on y. Really nice expression. Of course, the integral here just runs from 0 to 1. We couldn't go to infinity here. But here's a nice Laplace transform, and it is the Laplace transform of the Dickman subordinator. And this Dickman's original paper goes back to 1930. Apparently, I didn't read up a lot on this, but it's one of the very few papers he published. But it certainly did make a big splash. And this is how he derived it, by looking at this number of primes having a certain property. He came up with the Dickman function, and the function that's involved is in fact the density of this subordinator, so the generalization here refers to the fact that we have an extra parameter A in here. If I took A is equal to 1, then I would have the original Dickman function. So again, we have the density of this subordinator. Here it's evaluated at 1 on A constant. And here we have the CDF of that subordinator evaluated at 1. And they happen to have this property. Now, here's the magic connection. Here we have something that looks, well, a bit like this. We have a G instead of an F, and we have an alpha R instead of an A, but otherwise we have the same relationship. So what this suggests to us is maybe it's possible that we can use the property of the Dickman function to show what we want to show, namely that this part of the formula is in fact 0. And that is true. and that's how the proof is completed. The technicalities are, well, I've got an alpha and I have an R. I will let alpha go to 0 and R go to infinity in such a way that their product tends to this constant a positive, finite positive constant. Supposing it were, so I'm just conjecturing to make this into a little drama. Supposing it were the case that I took the limit as R goes to infinity in this form, and I in fact got 1 on A, I got this Dickman density here. And that this is plausible. In fact, it's plausible. You can go back and look at the Laplace transforms. The Dickman is the dx on x. The original, the g, is dx on x to the alpha plus 1. Remember, the constants are all in the right place, such that when you take this limit, you do in fact get this. Relationship. If that were true, in fact, it is true. Then, of course, because of the Dickman property, density equals CDF at that point 1. Then I would have that, and this is the limit of the CDF, and so I would have that the limiting version of this is equal to 0. Well, then maybe it's a bit of a stretch to say, well, maybe it's true not just in the limit, but maybe it is in fact true for every alpha and R, and it is in fact true, and that will conclude the proof. How do we prove this? Well, we have to go back to where it comes from. And the Dickman function has been worked on a lot over the years since 1930, and in particular, its connection with the PD alpha, the Kingman and Pittman developments of the Poisson Dirichlet distribution and process. And one of the kinds of properties which people familiar with Poisson Dirichlet will recognize the genesis of this as being that we can take this alpha RT, remember that's the sum of the negative binomial points, and it satisfies this identity. Here's alpha R plus 1T plus 1, multiplied by an independent uniform. We have to bring in a power here to make things work, make it right, but it satisfies this identity here. This identity here is a generalization of a known identity for the Dickman. Well, yes, the Dickman and the Poisson Dirichlet process in one of its forms. And that can, we can prove this. This is lemma. And once you prove this, then you have a proof of this. And once you have a proof of this, then you have a proof coming back here, you have a proof that this quantity is equal to 1, and we have magically gotten the limit under the integral without actually having to use denominator convergence, the bane of our existence, or one of them, by going through this route of noticing the connection with the Dickman distribution. This paper's been accepted in Advances of Applied Probability. You'll see it there. And there's a lot of discussion there, and we give all the technical details that, that will take you through the proof. What can you do with it? Well, it's meant to be a model for species sampling. It would be nice if you could actually use the distribution in some way. And actually, it's not so hard to compute some of the properties of it. So I'll just go back to number, wherever it was, number 3. Number 3. So this is the answer. This is the answer. And, well, it's still not all that pretty, but it's not so bad. Hey, this is just an exponential. And as I say, break it up into lambda less than 1, lambda greater than 1. That's just e to the minus x. Here, there's just a power of lambda. You're integrating over lambda. You've got this thing to deal with. That's the density of the subordinator, Dickman subordinator. Sorry, not the Dickman subordinator. This subordinator here, the one with the alpha in it. So there's still some computational issues to address here, but they can be done. Can be done, whereas I think you'll agree that trying to deal with this monster here computationally is well, you need to be a brave soul. So I'll come back to where we were. And we in the paper we give a couple of calculations. For example, we can you can get the moments of the of this distribution quite in reasonably explicit form. You see here what I skipped over earlier. Essentially the Laplace transform of this alpha RT object is of this form. It's just a reciprocal of a power of this particular. That's the exponent of the subordinator. Not such a hard thing to compute, and you can give this formula for the moments of the k quite explicitly. Mean and variance. So the mean and variance are here for various values of the parameters r and alpha, and you can look at these and you can derive some properties of the properties of the distribution. In the paper, we also have plots of some of the densities of the subordinators and so on. It's just about a good time to wrap up, I think. Couple of key references here. Andrew's book, and later on, some of his papers have explicit mention of the Dickman function in the context of the Poisson-Dirichlet process. And you can go to that for, of course, there's a lot more information on the Poisson-Dirichlet distribution process, and in particular, well, I won't say too much. Andrew's here; he can tell us himself if he wants. Famous Warren Ewens, of course, where it all goes back to the genetic application is Warren's paper in 1972, Sampling Theory of Selectively Neutral Alleles, very famous paper in this area. Firestone, Hulden, Sherwin. Geffen is the where we found the quoll data, phylogeographic population structure of tiger quolls. Fascinating paper, and they don't actually have my picture of the quoll there. I found that in Google. List of our papers. We reasonable to ask, have you actually tried to fit this thing to data? And the answer to that is yes, we have fitted it to data. Number of different sets of data, including the quolls data and some more extensive sets of data. That is not published so far, but it is available if you're really interested. It's one of these, I think this archive paper here, it's been listed up on there. And there's another paper by the three of us, which has also just appeared or about to appear in Stochastic Process Applications. The original Kingman paper, 75 actually, very famous paper in 1975, and a truly beautiful paper to read. Jeff Watterson's papers, which I perused a lot of the literature, and I read Jeff's papers in the process, and I should have read them long time ago, but hopefully I've made up for some of the derelict duty in recent years. So I'll finish there, and happy to take questions on anything to do with this.
Okay, thank you, Ross, for your talk. Maybe just give you a breath, just 1 minute before we ask question. I just would like to tell that most likely the next seminar will be in 2 weeks, and because we have a European speaker, maybe time will be slightly shifted later by 1 hour approximately.
So can I ask one?
Yes, and
Ross, the Ewens sampling formula, K was important because it was the sufficient statistic for the single parameter theta. You have 2 parameters alpha and R. Do you have anything as nice as sufficient statistics for estimating them?
The short answer is no, Andrew. No, and but maybe I can expand a little bit on it. You mentioned the theta parameter, and I think occasionally I mentioned PD alpha theta also as one of the Poisson Dirichlet's, which is derived again from Kingman and then later Pittman's work. We also can derive a PD alpha R comma theta version. And so that, in a sense, is a generalization of PD alpha theta. To come back to your question about the statistics and sufficiency and so on, the fact is, as I say, we have fitted this model to data, and that in itself turned out to be quite a job. And Sudi, who I thought was doesn't seem to be here anymore, did a lot of work in doing that. We managed to make it work, but what's missing from that is a lot of the statistical theory that you would like to see, such as consistency of estimated parameters and things like you mentioned, like sufficiency and asymptotic properties and so on. We don't know that at present.
Yeah.
yeah, I said it.
Yeah. Ross, first of all, it's great pleasure to see you again. I didn't see you since 1997.
Has it been that long?
When you kindly in Gold Coast invited us for dinner. And I remember this dinner still. Yeah. But
Thank
can you please go to, sorry?
I remember that dinner, yes.
Yeah. Can you go to your Formula 10?
Formula 10, okay. Yes.
Yeah. So this is expression for subordinator, which is sitting under the integral sign. And very similar expression appears when you want to introduce subordinators into explanation of Zipf's law.
Yes.
I wonder, this is coincidence or what is this? Very, very similarly looking, more maybe even precisely this is.
I think you're right, actually, and I wish Sudi was here because I wanted to direct these questions to her. But I recall, it's going back a little ways now, there was a Russian, there are papers that do mention this connection with Zipf's law. And I don't remember exactly what it was, but you're right, there is some sort of connection there with that. I don't remember exactly what it was.
Okay. Okay.
Can I ask a question?
Bob, good to see you there. And also, I read a number of your papers, and you know, I've developed a huge respect for your papers and Warren's and of course Andrew's and also Jeff's. I don't want to claim familiarity with them, but I did spend some time.
Oh, okay, great.
Sure.
Is there anything like a Chinese restaurant problem for these kind of processes?
Yes, there is. You can do that, and Yuguang and Sudi worked that out in quite a bit of detail. We never did. It's not actually been written down. I mean, we got notes on it, but the short answer is yes, can be done. And just to expand on that a little bit, as people may know, the one way of approaching this Poisson Dirichlet formulation is the so-called Chinese restaurant property, which they use. If you look up papers on so-called machine learning, you'll see a lot of talk about the Chinese restaurant. This is people come in and they sit down at the restaurant at a table, and they may sit down at the same table as other people are at with a certain probability, or they may create make a new table with another probability. And if you let that process carry on in time with constructed in a certain way, you will construct the Poisson-Dirichlet distributions in that way. And yes, as Bob suggests, there is a version of that for the PD alpha process.
So one more, if possible. So if you look at the Ewens sampling formula and its development, it's tied up with the Wright-Fisher model very much, and you could go to the Wright-Fisher diffusion model if you want the infinitely many alleles model and the Wright-Fisher diffusion, and so it's very tied up with that. But I think in the regular just two parameter Poisson-Dirichlet distribution, and also yours, it just doesn't seem to be a sort of stochastic model like the Wright-Fisher model behind it. Is that right?
Behind PD alpha R, you mean?
Yeah.
I know vaguely what you're talking about. Yes, there's Wright-Fisher, and yes, it's a diffusion limit of Warren's formula in a certain way, is my understanding. The fact is, we haven't looked at that at all. Haven't considered that at all. As I say, my knowledge of genetics is very limited.
Hi, Ross. That was a nice talk. So can you use this Chinese restaurant process-like description to get at this limit of the Kn or get some properties of it? I mean, that's how it works in the usual PD case. You find a martingale and the Kn.
Yes. The short answer is I don't think it would work, and I can't remember exactly why, but it's a logical way to go, but I don't think it would work with this.
So then another question is so then these limits of the number of tables as they go to infinity, they also show up in if you look at the whole partition and you look at the in decreasing order, and you look at the lengths in decreasing order and you scale them up, you see the same limit. So do you have some analog of that result?
Some kind of self-similarity, you mean?
Yeah.
Don't know. Haven't thought about that really. The way this thing derived originally was we were looking at jumps of subordinators, and that's how Kingman's original model was developed. And we modified that in a certain way, essentially by dropping off the big jumps. Dropping off R of the biggest jumps of the subordinator, renormalizing, and then doing more or less what Kingman did. And when you work that out, you arrive at this PD alpha R model. So because you've eliminated the largest order statistics, you no longer have the independence among the subordinated jumps, which makes a lot of things easy in the original formulation. So my guess is that that may not carry across, at least not in an obvious way.
Okay, thanks.